Hi everyone. We will briefly cover our homework 5 on latent denoising diffusion probabilistic models. We are working with diffusion models, powerful generators known for high-quality images. They learn to reverse a noising process to create data. While care, they are state-of-the-art for image synthesis, impacting creative tools and data generation. And our specific problem was implementing an efficient pipeline to generate class conditional images, telling the model what kind of objects to create. While diffusion models are not new, our focus was on implementing and integrating key modern techniques like latent diffusion and classifier-free guidance to build and understand an effective pipeline. So this was primarily an implementation project based on the description in homework 5 read up. We use the ImageNet 100 dataset for 130,000 images of 128 times 128 pixels across 100 classes. And crucially, we assume the use of operation VAE. Our approach starts with DDPM, gradually noise an image, then train a UNet model to reverse the process step by step, predicting the noise. As you can see, that's a basic structure of the UNet. But DDPM sampling is very slow, so we implement DDIM, a modified scheduler allowing much faster image generation with fewer steps. But working with 128 times 128 pixels images is computationally expensive. And in this case, latent diffusions can solve this. We encode images to a small latent space with a VE first and run the faster DDIM process there, and then decode back to an image. This will be much more efficient. And finally, for conditional generation, getting to get specific classes, we use classifier-free guidance of CFG. We train the model sometimes with class labels, sometimes without. So at inference, we combine predictions from both scenarios using a guidance scale W to steer the output towards the desired class without needing a separate classifier. We evaluated it using standard metrics like FID, where lower is better, measures distribution similarity, and also inception score, where higher is better, it measures quality and diversity. So that's our visual results comparison in a very early stage. We are still working on it, and we will get better results in our final reports, I think. So you can see the difference early here. Early DDPM results are often noisy. Our combined result approach, like combination with DDIM, with LDM and CFG, after like more training shows much better structure and coherence. That's a result of after 50 epochs. So that demonstrates the effectiveness of these techniques together. And the key takeaways, diffusion models need significant training time and patience. Initial results might be blurry, but DDIM drastically speeds up sampling. Latent diffusion makes higher resolution feasible, and CFG gives us control over generation. These combined methods are essential for building practical diffusion model pipelines. Uh, and And we want to let you know that this video and also this slides is still early stage of our training, and we will further employ more advanced techniques and also modify our hyperparameters to get a better model performance. And we will show all of this work in our final report. So future work would involve, more extensive training and hyperparameter tuning, and also we will explore more advanced training techniques and some advanced maybe model architectures of UNet. Yeah, and in conclusion, we successfully implemented key components, DDPM, DDIM, latent diffusion via VE and CFG. We learned about, the practical challenges of training and the benefits of these advanced techniques for efficiency and control. And we will show more of our results and our research in our final report. Thank you very much for listening.